Today we're going to talk about just some basic definitions for energy when we start with thermodynamics, and we're going to discuss the first law of thermodynamics and how we can apply that law to problems that have to do with heat transfer within a system. I'm just going to start off with a few definitions, and I'm going to go through these pretty quickly, so you can feel free to pause to get the definitions written down, or you can reference your textbook where you can also find them. All right, so the first is energy. So this is what this whole unit is about, and so we need to know what energy is. So energy is just the capacity to do work. It's a really simple definition. And so then what is work? Work is the result of a force acting across a distance. So if a rolling ball has energy, when it collides with another ball and causes that ball to move, it has done work. And so that's how we define work. Heat is the flow of energy that's caused by a difference in temperature. So heat flows is energy flowing from a hot object to a cold object, usually. Kinetic energy, we covered this back in honors, is just the energy associated with the motion of an object. And in the case of thermal energy, this is a type of kinetic energy, and it's associated with the temperature of an object. So the thermal energy is a result of the motion of the particles because they have some amount of heat associated with them. Potential energy is the energy associated with either the position or the composition of an object. So it's basically thought of as stored energy. And chemical energy is the kind of potential energy that we talk about often in chemistry. It's the energy associated with the relative positions of electrons and nuclei in atoms and molecules. And like I said, it's also a form of potential energy. All right, and then the law of conservation of energy says that energy can be neither created nor destroyed. I think all of you have probably heard of this before. And then finally, two terms that we haven't really talked about much in previous courses that you've taken with me anyway, are system and surroundings. So when we talk about energy changes, we're usually talking about energy moving from one place to another. And so we use the term system and surroundings. So the system is what we're investigating. So it could be a chemical reaction often, or it's whatever thing that we're talking about. And the surroundings are pretty much everything else that might be exchanging energy with the system. Now I'm going to go through just a couple of examples that use the system and surroundings new terminology that we just discussed. So the first one is you give a child a push on a swing. So in this case, the system, what we're interested in studying, would be the child on the swing. So both the child and the swing would be part of the system. And that means that the surroundings would be everything else in the universe. So you, the air around, all of that would be the surroundings. So in this case, primarily we, which is part of the surroundings, are doing work on the system, which is the child in the swing. So that means in terms of work, our sign is going to be positive because we're doing work on the system. Okay, so our W is going to be positive. There isn't very much heat that changes in this particular example. The only heat you could come up with maybe is friction from the swinging back and forth, which generates a small amount of heat. So we could say that the system itself is generating a small amount of heat, but it's going to be a very, very small, so almost negligible. So it would be slightly negative if we really wanted to include that. And so then, since that negative change is very small, and we've said positive work, then the total change in energy for our system is going to be positive because the energy is flowing into the system because we are doing work on the system. And the child goes from sitting still to swinging, so now they have kinetic energy. Now our second example continues on from the first. So after the child has been pushed on the swing, the child moves back and forth until coming to a stop. So in this case, the system is still the child on the swing, but they are losing energy overall. And there's really not any work being done on the system or by the system in this case. The swing is just moving back and forth. and eventually comes to rest. So all of the energy change in this case is from the friction of the swing moving back and forth, which slowly causes it to stop. So in this case, the system is losing thermal energy. So Q would be negative. I don't really see any change in the work, so that would just be 0. And then since the child goes from swinging, which is kinetic energy, to not moving at all and not really having any potential energy either, then our delta E for this particular example, for this system, is going to be negative. Okay, finally, we have sweat evaporates on your arm, generating a cooling sensation. So in this case, our system is going to be the sweat. So as it evaporates, it is going to require that bonds be broken, or intermolecular forces be broken between the water molecules that are holding it together in liquid form. So when sweat evaporates, it goes from the liquid to a gas. And if you remember from honors chemistry, that is an endothermic process, which means it requires energy. So if we're going to break those interactions, we have to put energy in. So work is being done on the system when that happens, and that heat is all coming from your arm in this case, because that's where the sweat is residing. So when it evaporates, it's pulling heat from your arm, which is why your arm feels cooler in the end. But the system itself is actually gaining thermal energy. And so when it gains that thermal energy, Q is going to be positive because the system is gaining energy. And then the work that's done is really just to move the molecules around. So they move a lot more in the gas phase than they do in the liquid phase. So work is being done in that sense, so that would be positive. And so then delta E for our entire system is going to be positive because energy is flowing into the system, which is why your arm gets cold, because energy has to come out of your arm, which is part of the surroundings, in order for that evaporation to happen. Now that we have discussed how these changes are going to happen on a qualitative level, we're actually going to do some calculations to see how this happens. So thermal equilibrium is the process by which heat is transferred between two objects that are at different temperatures, and when they reach thermal equilibrium, there's no additional net transfer of heat. Okay, and so we can actually calculate how much of heat is transferred in an interaction like this if we use the heat capacity, which is the system's ability to absorb thermal energy without undergoing a large change in temperature, and the change in temperature, or difference in temperature between the system and the surroundings. Okay, so we're actually not going to use heat capacity in itself that often because it's an extensive property, which means that it depends on the size of the system and the makeup of the system. So it's just a concept that we're going to talk about. However, specific heat is an intensive property, and so it's independent of how much or what the size of our system is, and we can calculate that using the equation here. So Q is heat, M would be the mass of the stuff that we're interested in, the mass of our system. CS is going to be our specific heat, and like I said, that's intensive, so that number is independent of how much we have, and we take that amount into account with the mass. And then delta T, again, is the change in temperature that the system undergoes. So now that we have our definitions down, we're going to go through an example. We did a couple calculations like this in honors, but I just want to review it, and we'll practice these calculations even more in the lab. Now, if we take the equations we just went over and go over a real example, so how much energy is needed to increase the temperature of 50 grams of iron from 25 degrees Celsius to 100 degrees Celsius. So the equation we need is Q equals M times C sub S times delta T. M is going to be our mass, which is 50.0 grams, times C sub S, which is our specific heat, which we can get from the table above. So since this is iron, we're going to use 0.449. And the units on that is joules per gram degree Celsius. And this is important because you want your units to always cancel out. And our change in temperature is going to be our final minus our initial, which is 100 minus 25, which is 75. degrees Celsius. And in a lot of cases, we have to change to Kelvin, but in this case, since it's a temperature difference, it wouldn't matter anyway, but the units in our specific heat is degrees Celsius, so we can leave that the way that it is. Okay, so if we multiply all those numbers out, we get 1683.75 joules, and that is too many significant figures. So if we look at the equation we started with, the most significant or the least number of significant figures we have is 2 in the 75 degrees Celsius. So that's how many we should have in our answer. So that, if we round, is 1700 joules. Okay, so that's how much energy it takes to increase the temperature of that piece of iron. Now, we can use the concept that any heat that is lost from the system has to go into the surroundings, or any heat that is lost from the surroundings has to go into the system. That's the law of conservation of energy. That's the first law of thermodynamics. So that always has to be true. Okay, so what that means is now that we have an equation for Q, we can put that equation to work for both the system and the surroundings and gain information that way. So here we have an unknown metal with a mass of 34.8 grams that's heated to 90.5 degrees Celsius. At that point, it's submerged into 75 mils of water at 24.5 degrees Celsius. If the temperature at thermal equilibrium is 27.2 degrees Celsius, what is the identity of the unknown metal? Assume that the density of the water is 1 gram per mil and that no heat is lost to the surroundings. Okay, so first let's set up Q for the system. So our system is our unknown metal. Okay, so the mass of that metal is 34.8 grams. We don't know the specific heat, the C sub S, so that's, we're going to just call X. And then our change in temperature is going to be our final temperature, which is 27.2, minus the initial temperature, which is 90.5. Okay, so we're going to get a negative number there because the temperature goes down. Okay, that is going to be equal to the negative heat of our surroundings. So the heat of our surroundings is going to be 75 grams for the water, since we have 75 mils, and we're assuming that each milliliter is a gram. And then the specific heat of water, which we can get from the table on the previous slide, is 4.18 joules per gram degree Celsius. And then our change in temperature here, our final temperature is still 27.2, but our initial temperature of the water was 24.5. Okay, so there we're going to have a positive number for our temperature. Okay, so if we multiply everything out on the left, we're going to get negative 2,202.84 times x, and that's going to be equal to negative the 75 times 4.18 times 2.7. All right, and if we solve for x, we get 0.384, and that the units on that would be joules per gram degree Celsius. Okay, and if you take a look at your table that's in your notes or on the previous slide, you can see that the specific heat of copper is 0.385, and that's the one that's closest to what we just calculated. So our assumption would be that it's probably copper, or it could potentially be some other metal that's not listed, but I wouldn't give you a problem like that. So from this, we calculated the specific heat of our unknown metal and determined that it's most likely copper. Now I just want to do a brief discussion of pressure-volume work. So we've talked about Q, which is the primary component of energy we're going to talk about in chemical reactions, but there's also pressure-volume work, which is when a force is caused by a volume change against an external pressure. So this would be like if you blew up a balloon, the change in volume does work on the surroundings, or if a reaction happens and gas is either produced or used up, then that would also be pressure volume work. Okay, so this is the equation for this work being W is equal to negative P delta V, so there should be a little negative sign there, sorry about that. All right, and we'll just do a couple of examples so that you can see how these work. So calculate the work done on a system when 6 liters of gas is compressed to 1 liter by a constant external pressure of 2 atmospheres. All right, so here our initial volume is 6, and our final volume is 1. So our delta V is going to be negative 5.0 liters, and our pressure is going to be 2 atmospheres. So when we plug that into our equation, we get that W is equal to negative 2 times negative 5, which is going to be 10 liter atmospheres. Okay, this unit of measurement isn't terribly useful, so we're going to use the conversion that there are 101.3 joules in each liter atmosphere, right? So that will give us 1.013 kilojoules, or just 1 kilojoule for the amount of significant figures we have. Okay, then the second question is a gas initially at a pressure of 10 atmospheres and having a volume of 5 liters is allowed to expand at constant temperature against a constant external pressure of 4 atmospheres until the new volume is 12.5 liters. So in this case, the work is being done by the system on the surroundings because it's expanding. So our initial volume is 5 and our final volume is 12.5. And our pressure here is 4 atmospheres. So we're interested in the external pressure that the gas is doing work on. So our equation here would be W equals negative 4.0 times 7.5, which is our change in volume. And when we multiply that, we get negative 30 liter atmospheres. And again, we'll go ahead and convert that to joules, or in this case, kilojoules is a little easier. So we get 3.0 kilojoules of work that is done on the surroundings in this particular case. So here we had a negative answer, so that's work done on the surroundings, and in the first one we had a positive answer, so that's work done on the system. Right, and our last problem here is a gas is allowed to expand at constant temperature from a volume of 10 liters to 20 liters against an external pressure of 1 atmosphere. If the gas also absorbs 250 joules of heat from the surroundings, what are the values of Q, W, and delta E? So we can calculate W just the way we have been in the last two problems. So W is equal to negative 1.0 is our pressure, and our change in volume here is 10 liters because we went from 10 to 20, so that's an increase of 10. And then if we multiply that out, we get negative 10 liter atmospheres, and we convert that to kilojoules. That's 1.0 kilojoules of work done by the system on the surroundings. All right, so that's our value for W, negative 1 kilojoule. And then for Q, it says that this system absorbs 250 joules of heat from our surroundings, right? So that's 0.25 kilojoules. And that would be a positive value because the system is gaining heat in this case. Okay, so then delta E would be just the sum of those two numbers. So we have negative 1 plus 0.25, so we get a delta E of negative 0.7 kilojoules.